I'm Adam Ilardi. I work here at eBay. I'm an applied researcher. Why do I choose eBay? It's a pretty cool company. They sell the craziest stuff you'll ever believe. There's like denim jean jackets with Nick Cage on the back, and this kind of stuff is all over the place. So it's definitely cool. The New York office is brand new. It's less than a year. And what does the New York office do? Well, we own the homepage of eBay. So the brand new feed is developed right over there. You might even see one of the guys. He's hiding. OK. And also, all the merchandising for eBay is also going to be run out of the New York office. So that's billions of dollars worth of eBay business run right out of here. So it's a major investment eBay has made in New York, which is really cool. So why you're here is to find out how we use Scala and Hadoop. And given all the data we have, the two pair very nicely together, as you will see. All right, so let's get started. OK, these are some things we'll cover. Polymorphic function values, higher kind of types, Scalesky star operator, some use of macros. OK, I'm kidding. I have no clue what those things are. So that was a test, all right? We're not going to be talking about that. We're going to be talking about practical uses of Scala. I don't know if any of those could increase revenue on eBay, but if they could, let me know after the talk. I'll be happy to hear about it. OK, so what we're actually going to talk about. Why Scala, why Hadoop, why we chose Scala and Hadoop, and I'm going to go through a lot of code. So bear with me, but I assume everyone is familiar with Scala, so it shouldn't be too much of a shock. All right, cool. OK. All right, so why Scala? So these are like the typical reasons why you'd use it. But the JVM is really important because at a big company like eBay, they've made huge investments in JVM technology. So they know how to scale it. They know how to monitor it. They have all these systems up and running that do this for you for free. So that's kind of a huge selling point, for sure. It's functional. So Scala is really cool. When I first saw options and ethers, I was blown away. You just can't get that in Java, and Scala gives you that kind of conciseness. It also is extremely expressive, so you say what you want to do, and maybe it doesn't make a lot of sense to non-Scala users. When I first saw Scala, I thought it was like a total mess, and I thought as I wrote things more in a Scala way, it became less readable, but I realized it was more expressive over time. So I think that's where you end up getting as you use Scala, which is really cool. How to convince your boss. You should probably just work somewhere where your boss already agrees with you. So that's my advice there. Yeah. So another thing that's good about Scala is a lot of people, there's tons of Haskell tutorials on the web. I feel like Haskell is maybe not going to break into the enterprise, but Scala has a chance. So by blending the functional style and object-oriented programming, Scala might bring people closer to that pure functional programming that Haskell offers without beating you over the head with it. So that's definitely cool. And all my life, I've always wanted a type-safe build system, and Scala finally delivered it. All right. OK, yeah, this happens a lot. OK, but I found it, so this is weird. I found it easier to write the bullet points on this slide than the last slide, which is odd, but there are certainly some complaints. The compile times can be very long if you have a large application. Ask anyone who works at Foursquare, and they will tell you all about it. Break backwards compatibility. So every time they release a new version, they'll break something. They're known for doing this. The Java util list is the same as it was in '94. That's not the case with Scala. Complicated. Again, I think that's kind of just people getting used to the functional style. I think over time, everyone's going to kind of get to understand it, and they'll realize what they're seeing is not really complicated. They just didn't quite know how to wrap their heads around it at first. This is one point that I found personally. It leads to madness. And I think Scala kind of goads you in a certain way. And let me try to explain that with some code. All right, so you're looking at a trait, which is a type class that kind of tells you you can create an object with some parameters, and it will only be created once, and if you ever try to change the parameters, it just won't work, right? So like you can see here, this is some crazy Scala stuff. I needed to make this covariant to like get the implicits to work. I had to make P a tuple to get like random parameters into this code. I use lazy vals here to kind of capture the fact that the thing is created once. And then here's a cool use of either. So like if it blows up, you get a throwable back, but it won't actually keep trying. So like the main use of this was I/O on Hadoop. So if someone accidentally tried to do I/O in the context of a mapper, this would prevent you from like crashing the node, the name node. So this is very useful if you've ever crashed a name node. And then down here, there's some code like how you actually get it, and it sets these parameters and then returns the lazy thing. Okay, cool. Does that make sense to everybody? Cool. All right. So then here's just how you use it. This is, just how you call it. You call it with that, and then, type inference figures out what you were asking for based on the parameters you passed in. I didn't show it the actual implementation of the implicit here, but it's around. Okay, so here's my point, though. All right, so this is used by one client class in my entire application. So show some self-restraint. Scala like goads you to make these really cool frameworks. It's like super expressive. You read all these blog posts about advanced features, and you just want to use them. But you got to watch out. So this is one of the things I got to say is really practical in Scala. You want to just get the job done. You don't need to do it the coolest possible way you can. And I learned that firsthand. All right, cool. So that sums up kind of like why we chose Scala. And it also blends into making it easier to use MapReduce, since MapReduce is on Java, as you all know. So for those of you that don't know what Hadoop is, this is kind of like a high-level view. So these are files. So these are just files. They could be in various formats. This is like an abstract class. And then they get sucked into mappers. And you can think of a mapper as like a map function in Scala. You just like map over a list of things. And then it spits out data here. It gets sorted. And then it gets merged. So then it gets fetched by these reducers. And it's merged and sorted again. And a reducer is like an aggregator. So it's not exactly analogous to a reduce function, but it's close enough. So you get keys, and you get an iterator over those keys. And my next slide will kind of make that a little more clear. So this is like a full MapReduce task. Like you could do no reduce if you want. You could do no map if you want. But this is generally what like a full unit of MapReduce work looks like. So it's pretty tricky. And to actually implement it, you need to implement these interfaces in Java. So like I said before, here's the map interface. You see a key, and you see a value. And then you output another key and a different value. So that's basically what a mapper does. And then the reducer, you notice key 2 from here came in as key 2 down here. And then you get an iterator of all the values of this that you outputted from before. So this is pretty simple. It is very low level, though. And it's nice to put abstractions on top of this to actually get any real work done. Imagine trying to do a join in this. It's probably difficult for people even who know how to do it in raw MapReduce, because it's just not natural. So that's kind of the problem there. As far as like you guys choosing to use MapReduce or not, I think this is kind of my prediction, but a lot of these algorithms that are coming out are like tuned for MapReduce, and I think you're going to see more and more of that. So while you could probably do things on a single machine at a smaller company, you're probably going to start to see like a lot of mind share around MapReduce. So even when you have like these medium-sized data sets, it still might be easier to use it just because of all the code out there that's available for you. All right, so how about eBay and MapReduce and Hadoop? Okay, so we have petabytes of data. We have 1,000 node Hadoop cluster, which is pretty big. And I mentioned before the multi-billion-dollar merchandising business that this Hadoop cluster supports. It also supports search, which is used quite heavily at eBay. And there's lots of users and items. Can't exactly say how many. All right, so how do I use MapReduce? So this is a good question. If you just Googled MapReduce and like framework, you'd get back a ton of stuff. And you'd probably be lost. So I remember the first time I saw the MapReduce website, it had Pig, Hive, like HDFS, core MapReduce. It was just overwhelming, right? So what do you do? The worst thing to do is probably write raw MapReduce. You'll spend a lot of your time in boilerplate, and it just won't be fun. You're not going to enjoy yourself. So what did people early on say? Oh, well, we'll just make an abstraction over MapReduce. And they came up with Pig, which is kind of like it's a scripting language, but it lets you integrate Java code and other code with it. Then they came up with Hive out of Facebook, and that was basically SQL queries. So if you just need to know the average of a column, like use Hive. Don't go crazy. But there is a lot of setup to get Hive going also. So this is where the picture starts to get a little bit better. We land on Cascading. Cascading is a Java framework. It's built over MapReduce. It kind of abstracts the whole mapping, sorting, reducing bit. And it lets you write kind of natural code. And you're going to see some examples of this. This is also maybe not the least amount of code you'll ever have to write in your life, but it's very maintainable. And I'll talk more about that as well. Some other options, maybe Scooby. You guys are Scala people. You probably heard about this. It's basically a MapReduce framework written in Scala. And remember when I talked about madness before? I think a lot of the things in there were like to scratch some itches. Like you have to compile it with the Y-dependent types flag. You know you're like in different territory. So those guys, I think they're doing great work. But they're definitely still working on it. And here we come to the punchline here. It's kind of like scalding is kind of the way we've evolved here. So we have, to be fair to history, we have a lot of pig code, we have a lot of cascading code, and now we're creating a lot of scalding code. Okay, so how do you make a decision? All right, here's a kind of long quote. I'll give you a moment to digest it. All right. So the basic idea is some guy built his house on sand, and then flood came. You know, floods come a lot when you're in software engineering, and it got washed away. Except for the guy who built his house on, you know, like stone. It's not going to get washed away. Okay, so I believe, all right, that scalding combines the best of pig and cascading. And you're going to see this in a moment with some examples. And you might say during this, like, why we didn't go with Scooby, because it's raw Scala. And I think part of the reason is scalding is based off cascading, which is like an extremely strong base. So the abstractions they built there have been like tuned over years. And there's a company backing it. So everything about it is like really solid. I think I ran into maybe one major bug, and it was fixed in the next version. So I trust the cascading people. Pig people too. I do trust them as well. Some of the Scooby stuff was a little immature, and it is getting a lot better, but it's not perfect as of yet. Maybe one day it will be better, and I'll bring up some examples to contrast it later on. Okay. So here's some good pig. All right, so remember that MapReduce API I showed you before? You don't have to write any code that does that. This is some good pig code. You say, hey, load me this file, give me some field names, do some filters. This sounds a lot like Scala right here. And then you could output it. And then over here, you could do some other stuff, you know, get some other fields, and then store it somewhere else. Another thing pig is like doing joins and group bys. So joining in that other API is like clearly unintuitive, and you have to do some major hackery to get it to work. So in Pig, you could just say, hey, join these two like variables by like some value, and it just magically works. So I understand why everyone kind of like flocked to this early on. So here's some bad Pig. All right, so this is the downside. Let's see here. So what's someone doing here? It looks like they're taking a Perl script and sending it to every node on the cluster. So this may not be a good idea. I mean, do you even know where that Perl script is stored? I mean, it could be in someone's home directory. It's definitely in the scripts variable, but I don't know. That looks a little shady to me. All right, so actually, I don't actually know what this code's doing because it just says NV terms, stream some data through it, and I get it back out. So, you know, without a comment here, I really have no clue what this Perl script actually does. So this is not so good. Another thing is you can add Java code to it. So right here, you'll notice some Java code being called. Again, I really don't know what this Java code does. I'd have to actually look at the source. I'd have to find the jar. And that jar is as well, like, probably imported via some script like tag like this. And then it's exported to everything on the cluster. Okay, so another problem with this. So you don't know where your source is, and you wrote a bunch of scripts that look like this. And now you decide, right, well, script A now depends on script B. And then after that's all done, I have script C to run. So how are you going to string these things together? Well, that's kind of a problem because if you don't always want to run A, B, and C in that order, maybe A is cached and it gets updated every so often, you're going to need to actually like string them together using bash scripts or something like that. So you'll be like, oh, there's no way people do that. So that is true. There are extra frameworks built, like LinkedIn has Azkaban, which basically allows you to construct a DAG of all your dependencies and lets you kick off that job. So this is just another layer of complexity that you need to like handle if you're going to write Pig code. So that's kind of that. I just mentioned about this scheduling, DAG creation. You know, you need to use some external framework or roll your own. And it might be tempting to just roll your own because it's quicker and easier, but you end up then with all these dependency problems and nobody knows what's going on. I could say this from some experience. All right. Okay. So cascading rocks. All right. I'll remind you again what it is. It's a Java framework. It basically treats MapReduce as a stream of tuples. So you have tuples in Scala. Imagine that a stream of them is just flowing through various pipelines. And that's what cascading is at a very high level. Look, it kind of addresses two of the big problems I have with Pig also. So it supports really large workflows. So I can use all the abstractions available to me in Java, which are plentiful. And I could write code with all of those. Some really cool things are the automatic DAG generation. So based on how you structure your code in the Cascading Framework, it will compute all the dependencies for you. And it will like actually output a graph of everything that is there, which is super cool. If you just show somebody that, they'll be sold. Also, parallel executions. Since it computed the graph of everything it needs to do, then it could basically choose to do things in parallel. And Pig can't exactly do that out of the box. You'd need Azkaban to do that, or some additional framework. Okay. Also one other thing is because of the DAG generation, you can kind of cache files. So if there's like a really heavyweight job that needs to run, you could cache it on the disk, and then you don't need to run it every time you kick off dependent jobs. And I'll show you an example of that later on also. Okay, so here's some code. So basically here I'm saying, hey, create a new master pipe. I give it a nice name, and then I'm going to say filter some URL encoded strings out of this. And here's a field name I'm passing to it. Now, what is actually in this pipe are a bunch of tuples, and they're all named. So here's a name of one of them. So there's a lot of good things about this. This is pretty clear. It's Java code. If I hold down Control and click in Eclipse, this will take me to the source. And that's a beautiful thing, especially when you're coming from Pig, where I couldn't exactly do that. And then down here, it's doing another thing. I'm saying like filter more inappropriate queries. And you'll notice it's kind of like building a pipeline. So like this variable is passed into this thing, and then it's reassigned. I just realized it couldn't be reassigned because I made that a val. Anyhow, and then you'll see down here that it's taken again, and then you're going to group by. So you could say, hey, I know I have these fields, group by them, and then give me that iterator. It's that same iterator you saw back in the raw MapReduce API. So you could also do things like secondary sort. That's what's going on here. Does all this make sense? Cool. All right. Oh man, what did someone do here? Okay, so this is the output of one of those DAG calculations. Now, you may argue that possibly this wasn't the best use of MapReduce, but the fact is it was very easy to do in Cascading. And because of all the abstractions it gave me, it was very easy to do a loop and cause all these things to happen. And then they get flowed into there and there and there, and it's finally outputted. So this is really cool. And it'd be very difficult to manually put this into Azkaban, I could imagine. Again, you'd probably argue I shouldn't do that, but this is definitely cool. All right, so cascading issues. All right, so I can't really think of too many. This is an old IBM joke here. Anyways, the point is the only thing I could really think of that's not good is you have to still write a lot of code because it's in Java. People kind of complain about the verbosity of Java. And also, you have a lot of pipelines. It's not always super clear. So I guess you could level that complaint against it. But again, it's definitely a good workhorse. If you were to like reach into the bag of Hadoop tools and pull out cascading, I don't think anyone would fault you. Okay, cool. So now it's time for scalding. All right, so welcome back to the world of Scala. And this is where scalding really makes things cool. So scalding is a domain-specific language written on top of cascading. It's done by Twitter. They've done excellent work here. Okay, so let's just look at this code for a little bit here. So it takes some arguments, it extends a job, that's like in scalding. And then here you're saying, okay, get me a text input, and that's the file name, you know, in the args. And then now you're doing something that's pretty Scala-like here. So before I go into that, this is counting words. So you may have seen this example countless number of times. So like Hadoop is the best framework for counting words ever built. And you'll see it implemented over and over and over. So it's a very good example, and it really kind of illustrates the power of each abstraction that every given framework adds. So what do you got here? You got some flat maps going on. It takes a string. So assume this input was like line number and then some text. And then I use this tokenize function to spit out an array of strings. And you know what flatmap is going to do here? It's going to like create more and more tuples that come out of this. So then you're like, oh, okay, I have all these words now, and I just want to get their size. So I group by them and do a size, and then I write it out. I think what's important to note here is that you're writing code that's kind of close to what you would actually do if you were doing it in memory. So that's really what the goal is here. They don't want you writing like streams and pipes and all these kind of things. That's not really a natural Scala construct. They want you to be reminded what it is to write like Scala code, and then you could be more productive. So you start seeing things like flatmap, you know what to do, as opposed to like some tuple named every. You'd be a little bit more confused. So to be fair to Scooby, it has a very similar interface. But again, since scalding is built on top of cascading, you're basically just proxying down to cascading functions, which are really well designed and work excellently. Okay. All right, so we chose to use scalding. So there's still some problems. We have to use it at eBay. We have these gigantic tables on HDFS that have 100 or more fields in it. And if I want just one of them, I'm extremely confused about how to get it often. So if you just had to know the index of it and someone changed it, all your code would be kind of screwed. So that wouldn't be good. So what could you use scalding for? You could definitely reduce the boilerplate of actually finding fields in HDFS tables, if you want to call them tables. It's super extensible. So you'll see an example of how we extended scalding to do a lot of natural things that make our code a lot more readable and definitely more extensible. So this is a good point. New hires. So there was a big argument about whether or not people who get hired into doing this kind of work should start off directly with one of these frameworks that's super high level to get them productive right away. So that's kind of like why we were pushing towards Scooby and scalding. It's a lot less intimidating than going right to raw MapReduce or going right to cascading. The problem is when you actually get to do something complicated, you run back right up against the wall of, I need to know how MapReduce works. So I think it's good that these things are coming out, but the thing it abstracts is still very important to know. And I'm not sure we could get away from that now. I mean, maybe in time. Okay, cool. So practical scalding usage. So they use the pimp my library pattern, and we just took that one step further and did it again. This code-generated boilerplate. So we actually just wrote a Scala program that like parses over XML definitions of tables and spits out a very clean interface for accessing those tables. And I'll show you an example of that in a bit. So this is super important. If we did this, everyone was just like clamoring for it because everyone had this same problem of like, I had to look at this table and I don't know what fields I need. And now we give them all consistent names like based off this XML definition, and everyone's super happy. All right, so cascades. Cascades are a cascading feature where like one cascading flow depends on another flow, and you could do special things. So you could say if flow A was stale, then regenerate its data, and then give it to flow B. So that I'll give you an example of a little bit later, but that's not in scalding. That's just in cascading, but I submitted a pull request and they accepted it, so it is now going to be in the next version. So that's very cool. Traps. So often you're producing a lot of data in HDFS that is just garbage. So a data warehouse team has to put it there. There's also like clickstream data. People put crazy stuff in fields they're not supposed to, and it all ends up in your data warehouse. So what a trap does is say, hey, I was expecting this to be an integer and it blew up. Just throw it in some separate area and I could go back and look at it later. So these are critical for like making these things work and debugging, because debugging a MapReduce job is very difficult. As you will see, I'll get into a little bit later also. And then another important thing is testing. Scalding actually has like an in-memory test framework. So you could say like, given these inputs, like you actually define the tuples that are your input, and then you define the tuples that are your output. It will run through your entire job and then just validate if it worked. So this is extremely important because once it's on the cluster, like anything could happen, and it's very difficult to tell if you had a rounding error when you're adding like millions of numbers together. So it's super important to do things on a known data set beforehand to make sure you're getting the actual results you want. Okay, cool. All right, so I'll walk you through some of the code we wrote over here, and I had a large hand in it. So this pipe boilerplate class, okay, so let me just start over. You saw beginning that extended job before. So now we have an eBay job, which I broke naming convention for branding purposes here. And then that extends that job, and then I mixed in this pipe boilerplate. So you'll see an example of pipe boilerplate later, but that's basically that code generation to get rid of all the like having to know where every field is on HDFS. All right, and then over here, here's where we like extend the rich pipe. So the way scalding is implemented is it has this thing called rich pipe. So every time it sees a pipe, it turns it into a rich pipe, and that gives you all those kind of cool functions like flat map, whatever else. So what we did was say, hey, well, I'll just take that a step further, and there's a lot of like common things people at eBay do over and over again, and they're often annoying. So unfortunately, some of the more annoying things are obscure. So like not everybody knows them, and then you have to go digging for it. So what you do is basically you define a trait that imports the various DSL classes, and then you just define a pipe. And due to the magic of mix-ins, it ignores this when it like mixes it in, which is really cool. And then you could define all the kind of really complex functions you want. So whatever mind-blowing code you have that like you think people just can't handle, you just wrap it in this abstraction, and then you could call a really complex function exactly like we called flatmap. And this is extremely useful. So one example was we wanted to compute quantiles over like a given category and the items that sold in it for what price. So we just extended the rich pipe and included a function like compute quantiles in category. So if anyone wants it now, they could just use it automatically, which is really cool. Okay, so it reads, it ends up writing code like this, which some might argue is too readable for Scala, given the, that Martin Ardisky tells you to use single letter variable names and things like that. So you end up with code that basically says, hey, I want to get the transactions pipe, and give me some default path logic, and we've defined all that too for you. And then this is where the magic kind of happens. So every field name is in this pipe at this point, and then I say, hey, just give me the fields I need, and you just toss out the name. And to find the name, you could just look through the code. And there's actual like a concrete class that was also code generated that has the name like checkout transactions. So now I have exactly the fields I need. And then I use this in a single job. This is not shared code, but I did it to kind of make the high level flow very readable. So over here you say like, so to give you some more context, this is actually a user preferences job. So it says like, does this user actually like brand Coach? And then give them an affinity towards that piece of structured data. So in order to kind of encapsulate that entire process, you just say like, it does a few things. It counts how many times the user interacted with that piece of structured data, and then it does a score calculation, and then it does a confidence calculation. So if anyone came up to this code, they could easily just like click into each bit and then find the actual calculation that I did. To be fair, there's a couple of lines that I left out, but it's generally very simple. And your code can end up looking like this. So remember back when you saw that like pig code, where it was just like, this is why I say it combines the best of pig and cascading, because the pig code did look somewhat similar in terms of the use of like filters and maps and group bys, but it's not in Scala. So inside all these functions, whenever I bring a piece of data into memory, I could use all the abstractions Scala has to offer. And those are even more plentiful than Java, which kind of brings me back to that madness point. So don't go too crazy. Okay, cool. Here's some other interesting things we've done. So collaborative filtering is like typically very difficult to run on a large data set. So there are libraries like Mahout, but they have an extremely large learning curve. It's like the examples will run out of the box, but then as soon as you're like, okay, I'm going to plug my data into it, you start getting exceptions, and you have to go to the user group, figure out what's wrong. I hope this is going to get better in the future, but it's not as user-friendly. So I've noticed a lot of cool things happening in scalding around this space. So one thing is like Edwin Chen, one of the guys who worked at Twitter, just put out a blog that did a very simple item-to-item similarity algorithm, and it's extremely extensible. You basically just override the input pipe, so you say, give me this input, and then you could do some output munging too, and it just works. So like the barrier to entry to running collaborative filtering algorithms, which are typically difficult has just like dropped down to almost nothing if you have a Hadoop cluster. So this is extremely powerful. And a lot of the abstractions that the scalding guys are building in go with the same principle. So there's another library called Algebird, and it has all sorts of cool things. Like one is a monoid that just gets average, standard deviation, and count. And it does this, cross MapReduce, but it doesn't need to bring all the data into memory at once. So they're implementing a lot of algorithms like that are smart enough to work on streams of data instead of viewing the entire data set in memory at once. And that's what using scalding is really good for. So you're kind of leveraging those abstractions to do more and more complicated things, but you're doing it in a simple way. What else? So to be fair, these methods of collaborative filtering are a little less precise than some of like the other state-of-the-art methods. But I think the point is that like if you could get that up and running, you could make something better for your customer tomorrow rather than like 6 months from now, which is super cool. And if you're super interested in machine learning, one of my colleagues, Chris Sievers, is giving a talk at Scala, at the Scala conference about this. And I'll post a comment on the board, but definitely check it out. Okay, so here's another cool piece of tech we built using Scala and Cascading. This is structured data importance, so it's kind of like a user has affinity to a certain brand. But in aggregate, what do people generally like decide to shop, based around what aspects do people decide to shop? So if you go to the store, do you first look for the brand, or do you look for the color of the thing you want, or do you look for the size? So like all of these are various aspects, and this kind of represents the supply we have on the site. So this job is kind of like important for two reasons. Like if bag depth was really important but had no supply, maybe we need to tell people to start like listing it more. And also if you notice the eBay search experience, you'll see a left navigation, and there are certain aspects you could actually click on, and then when you click on them, it filters the results. So above the fold, you only have opportunity to show like X number of things. So you have to like figure out what they are. So remember that crazy DAG I showed you from before? That's this job. And the reason that DAG is so crazy is it's a linear model that's computed completely on Hadoop. The coefficients of this model are not learned on Hadoop, but they very well could be. And then you just plug it in, and then it'll compute your model for you. So you could do things like that pretty simply without like resorting to frameworks or anything like that, which I think is pretty good. One other interesting thing that this job used is structured data extraction. So we have these like other machine learned models that are used within Hadoop context. So say you're like streaming over a bunch of search queries and you want to know, did that person mention a brand or not? So you could build a completely offline model that is like partitioned in some way, and then you use Hadoop to stream over this massive data set. So you load that machine learned model into memory, and then you just stream all your data through it and output more and more tuples. And this is like, when you have 1,500 like machines doing this for you, it gets done a lot quicker than you could ever imagine like doing it on your own. So you could scale simple models across huge amounts of data by using Hadoop and MapReduce. Which brings me back to the earliest point of that trait you saw, to do I/O once. That was because of this. So I had seen it had been used once inside the context of a mapper. I realized it definitely could cause problems. So you only want to do that I/O once. So that's kind of why that earlier trait was created as well. Some other cool things you should do, like practical concerns, especially with this job, was like this graph was built out of a SQLite database. So often your MapReduce jobs will like churn over immense big data, and then at the end of it, you end up with something that's like very small, and you're like, I want to ask some more questions about what I outputted. So you just chuck it in a SQLite database, and then you can figure everything out from there. Okay, cool. Here's a particularly cool piece of Scala code that I recently wrote. We did some Markov chains to investigate the buying patterns, and it's about 50 total lines of scalding code. But here's the kind of meat of it, and this is why you can't do these kind of things in Pig, right? So this is all in the context of a reducer, but I've used like all the cool stuff Scala has to offer to basically compute this in a few lines of code. And these lines of code here are like almost identical to what I wrote to test it in a single threaded context. And then I just basically copied and pasted it into a reducer and then ran it on the cluster. And the first shot, it came out with the data I wanted. A cool thing here is how it like, so a Markov chain is just like, given your current state, what's the probability you will advance to the next state? So you could imagine this state as you bought something and you're going to advance to the next state of buying something else. So what you're looking at here are like the purchases that somebody made, and then we're figuring out the probability that they're going to move on to the next state, which is like you're going to buy the next, what next product, right? So this is pretty useful. And then I just use this cool trick to like get the first time probability here. So you're not looking at MapReduce code, raw. This isn't like scalding code. This is just Scala that's being used. Does that make sense to everybody? Any questions? Okay, cool. All right. Here's a very interesting job. Again, we had to mine search queries. So there's billions of search queries associated with a given user on eBay. A lot of the queries they make are done before they're logged in, so they're not fully associated with a user. But if you want to know what are the top queries for a user, like various use cases could be like, it's like a saved search type of thing. Like here you search for these things a lot. Maybe you want to follow it, something along those lines. So this job here really kind of took all the lessons we learned about Hadoop and implemented them. So these 20 billion user queries are not in a single place. They're mixed in with clickstream data. So to actually get to them, you have to parse over tons and tons of clickstream data. So it doesn't make sense to every time you want to do that, like look through the fact that you clicked on an item, clicked the back button, did something else. That's just useless. And there's like petabytes of it. So what you do is you go over it once, dump it to a known location for a given day, and what cascading allows you to do is basically say, hey, if this day is computed already, just like go on with your life, don't recompute it. So that's the perfect example of like a great abstraction cascading gives you. So now we have all these queries that are on the disk and they're isolated. What do we have to do? So one typical thing is like deduping them. So like you could run some tokenization on them. This is actually what we did. Ran some tokenization, and then we used like this unique function in cascading, which basically sends every query to a bunch of mappers, and it keeps a few in memory and says, hey, if I saw it already, like get rid of it. And then it pushes everything to a reducer, which has the effect of deduping naturally also. So that is pretty cool. So now you've deduped a lot of the useless queries, but you've retained the ones that are the newest and the ones that are the oldest out of all of those. So now you can rank. So you could say like, if someone has searched for something a year ago and then they did it 6 months ago and then they're still doing it today, that's probably pretty important to them. So you could write a ranking function around that. It's very easy to get like mins and maxes of things in a MapReduce kind of context. So that worked out really well. Another thing is like some kind of like fuzzy matching, right? Like given a user did X number of things, you rank the top bunch of them, and maybe you say like, well, these two things are really the same, but since you've like reduced your data set down so much, you can now actually like run a more comprehensive algorithm to say like these two pieces of text are exactly the same. So a lot of these jobs, like you'll see this a lot in MapReduce, is you start out with a lot of data, you whittle it down, you do the easy things to get what you want, and then you could finally get it into a compact enough representation where you can do something like really cool to it. which is pretty typical. So this brings me back to a point. I'm going over 20 billion user queries. If some of them are buggy, how the heck am I going to be able to tell? So I can't just attach a debugger to every JVM that's running in our Hadoop cluster. That wouldn't work. So what you can do is count things. So Hadoop gives you this abstraction called counters, and it lets you just, as you see something, you increment. So what we did was we put counters in for bad situations. So anytime you saw a bad situation, you got a count. And then when the job ended, Cascading gives you a list of all the counters that ran and all the flows, and then you could run validators over it. So this is a good use for Scala Z validation, which is pretty cool. You could just run validators over all the flows that were ever done. Okay, so you have a bunch of jobs, you have a bunch of Scala code running these jobs, and now someone asked me I want this updated daily. Okay, so what do I do here? So this is pretty simple. This is how we do it. Because everything is Scala and cascading, we just basically use Jenkins to compile it, and then we say, hey, Jenkins, go and send that compiled code over to the Hadoop proxy. And because, like I mentioned, it handles all this dependency of various flows and jobs within this Hadoop context, it's easy just to package up a single jar and send it over. And you don't need a complex scheduling framework like Azkaban necessarily. Depends how crazy you go. You could just make a simple Jenkins job that says, hey, trigger this bash script that runs this job. And then you wait on the status. And then when the status is complete, you just say, hey, Jenkins, OK, go back there, tell it to download the file. So Jenkins compiled it, sent it over. It then said, execute it, OK. And then it said, oh, all right, it's done. OK, download the file. And then sync it over to these batch database load machines. So these are just VMs that we have. And once they're there, then Jenkins also kicks off another process that says, OK, get this data into the database. And that's where our data goes into Cassandra. So those user profile, these user preferences I talked about before, which was like brand X, that goes in Cassandra. And various other stuff, like that aspect important stuff, goes in MySQL. Same thing with those user queries. And some legacy stuff goes into Mongo as well. All right, so I think that about wraps it up. Does anyone have any questions? You, sir.
You look at the H catalog for that metadata extraction you were describing, what fields are in what files?
Yeah, what do you mean about the catalog? Sorry.
There's a product now in the Hadoop ecosystem called H catalog, which is the metadata to describe what's in the.
Oh, okay. So we. Oh, okay, the question was about H catalog and had we looked at it. So to be honest, that kind of decision's out of my hands. The Hadoop group is a bunch of people, and they have things that support like Teradata and other kind of big data warehouse stores. So they have their own system, and I don't exactly know what it is. But it publishes similar metadata, which we used for code generation. So I could imagine you could do the same thing with another suite of software. All right, free light bulbs for questions. Okay.
In terms of type safety with scalding, it looked like you were putting field names in quotes.
Oh, yes, you're very observant, sir. Okay, so the scalding, the API we're using currently is not type safe. So the only type safety you get is actually once you're executing code. So back here, now I get type safety, but that X variable where I'm getting stuff out of, there's no type safety on that. There is a type safe API that's in development, and it basically lets you pass classes around. So it will always validate that okay, you gave this segment of code a Atom class, and you're getting back a foo class. And then it wires type safety throughout the whole process. So I don't have an example, but you could imagine there being types on every one of these things, like count user interaction, return some type. And that's what they're doing with the typed API. Yeah. You, sir. So we use all sorts of stuff. There's like sequence files, and there's TSVs. So a lot of this data is created by this data warehouse team, and we're kind of stuck with what they give us. But when we sample it, we've done a combination. Like occasionally we use sequence files and a serialization format, but often we'll just use TSV because I could go to it and look at it, which is actually quite valuable. So we tend to gravitate towards like readable text. Cool. Sorry? Multicore? Oh, so, okay, so we haven't done any kind of multi-core processing within the MapReduce flows themselves, but you certainly can. So all these frameworks let you actually get pretty close to the metal of MapReduce, and there are methods in there where you could override, and it would let you like do multi-core processing. So one example is like, if you just aggregated a bunch of stuff and you know it fits in memory, maybe it's faster to do multi-core processing on it. We haven't run into a situation where we necessarily needed to do that. One of the problems with doing that is you kind of starve everyone out. So like, if I go nuts on my like one reducer and I'm sharing that node with a bunch of other people, which is very common at eBay, we have like many clients of the Hadoop cluster, you basically like consume all the resources of that reducer. Hadoop doesn't have very good boundaries between like different tenants. So if one tenant takes out the system, it like kills it for everyone else. So that's kind of why me personally, haven't done that. But there's definitely, you could do it. Yeah. Sorry, could you say that louder? Queuing system? Yeah, so there is a queuing system that like you could kind of give people certain priorities over other people, but you don't have any control of where the task ultimately gets run. So the task is going to be scheduled out by the MapReduce framework. It's going to land on some worker, and if you starve out that worker and start failing everyone else's jobs, there's nothing they can do about it. You.
Last slide on automation, using scalding to export from HTML to Cassandra and Mongo.
So that's a good question. No, we're using Python because we like Python as well, and it was very easy to do. We were familiar with it. But you certainly could use scalding. I think this kind of like general framework just supports anything. I do have one job that creates Bloom filters that uses Java. I certainly could have done that in Scala. I just didn't. Yes?
What about version? In Hadoop in general, it's been very hard to move to a new version. Hadoop has been stuck
Yeah.
for a long time. How is that worse in scalding? I tried to take a Git repository down recently, and it didn't build.
Okay, yeah, so the question was, how does it play with different versions of Hadoop? I believe, so I've run scalding code on like 0.22, if I recall. We're on a newer version of that. So it does work. I was able to get it to work on like an older version of MapReduce. And I know there's two specific MapReduce APIs, and it does support both of them. There's like the old style. If you actually look through the MapReduce code, you'll see like an if statement, like use new API, use old one. So you can get it to run with the old API code. I'm not sure exactly what the problem you ran into was. It's possible they didn't cover all the cases, but generally it's kind of friendly, I found. So with the stuff we do here. Yeah. Yeah, sorry. Oh, yeah. Yeah. So yeah, it's definitely interesting. Also, cascading is built against specific versions of Hadoop also. But I think in general they try to be friendly to the older versions because like a place like eBay gets stuck on an old version and you actually like need to take the cluster down to upgrade it. So it becomes very difficult to upgrade like seamlessly. Like you can't just, you have to actually take the thing down. Cool. Any other questions? Yeah.
Do you use
Yeah, so Hadoop supports like gzipping, I believe by default, and it also has a splittable compressed format. The name is escaping me, but definitely the data we use is zipped up. But the thing is, yeah, when you choose to use compression on Hadoop, you have to keep in mind splittability. So when you're trying to like farm tasks out to mappers, if you can't split at arbitrary points of a file, then you can't actually like get it to a mapper without truncating like something useful. So yeah, we do use, I believe we don't use the splittable one, but I'd have to double check. Yeah. Cool. Yes?
Did you learn Scala before you scalding?
Yeah, so we had originally started using, so I had learned Scala in conjunction with cascading, to be fair. So we originally just had Scala calling cascading directly. So we didn't write anything in Java. And that's kind of when I started picking up Scala. So, you know, I'd say, I think like my early Scala, to be honest, looked a lot like Java. So like I look back at things I did before and I see myself like incrementing data into mutable lists. And I'm like, what the heck was I thinking? But that's kind of the evolution I took over it. And then when I started getting better and better at Scala, I found cascading, scalding more and more appealing because it kind of melded with the functional constructs that I was learning. So, cool. Yeah.
Have anybody here used the Avro formulas, and do you have any opinion on that?
Yeah, so the guy I mentioned who's giving the talk at Scala Days, he's a big proponent of it. And so you could imagine like all of our data warehouse tables are stored in like this type of serialization. And that would make things a lot easier in certain cases. So people do use it and they like it. I think we just haven't jumped into it because we haven't had a real strong pressing need to do it. But it's definitely something to consider if you're starting fresh and like writing tables into Hadoop that many people are going to be using. Like Avro is it's a good choice. Cool. All right, anyone else? You know? No? All right, cool. Well, thank you all for coming. I hope this was informative. If you want to follow up anything new about eBay, like go to our website. We are hiring, of course, and we love Scala here. We are also trying to get Scala into more visible places in eBay. So for instance, all the recommendation services currently run on Java, and we're like experimenting right now. People are pushing code that is going to get Scala like serving recommendations. So we're experimenting it with in more places than just Hadoop, which is really cool. So thank you, and good night.